In general, there are two groups of satellites, those that orbit like this around the equator, and those that orbit from pole to pole. Almost all the satellites that orbit from pole to pole are at low altitudes. These photograph and examine the surface for analysis of crops, for weather, or perhaps for military purposes. Each orbit may take, say, about an hour and a half. As they orbit, the Earth is turning beneath them, so over the course of 24 hours they can examine the whole of the Earth's surface. Satellites at a higher altitude will orbit more slowly because the circumference of the circle is greater and the pull of gravity is smaller. A satellite can be launched and put into orbit above the equator and rotate in the same direction as the Earth. If we calculate the height of orbit very carefully, we can place the satellite in orbit so that it exactly matches the rotation of the Earth. The satellite follows the Earth round, always staying over exactly the same point. This geostationary orbit is essential for communication satellites and for global positioning satellites. We can calculate the matching speed, height, and orbit time of every satellite to match its purpose. If the satellite is in stable orbit, then the force of gravity must be exactly equal to that force needed to provide the acceleration to the center for circular motion. We look at this both in terms of angular velocity and linear velocity. The force required to maintain circular motion is mr omega squared, where omega is the angular velocity. Lowercase m is the mass of the satellite, r the radius of its orbit from the center of the Earth, g the universal gravitational constant, and uppercase M is the mass of the Earth. Thank you for watching. The full lesson and many others are available for download and on DVD at the website.